All right, so let's move on to this idea of theoretical probability. Okay, so we're going to come back and kind of talk about the example with the colored cubes. So each fraction is the theoretical probability of choosing a particular color of cube when the cube is randomly drawn. Okay, it says when all the possible outcomes of the experiment are equally likely, then the probability of the outcome is 1 out of the total possible outcomes, right? An event is a collection of outcomes, okay? Kind of like a sample space, right? When the outcomes are equally likely, the theoretical probability event can be expressed as number of favorable outcomes over number of possible outcomes. Again, this means total, right? The total outcomes and favorable outcomes. Well, favorable means what event do we mean to have happen? And this will make more sense when we try some examples. So, drawing a blue cube, the theoretical probability is 10 out of 40, or 1/4. The probability of blue is the number of blue cubes out of the total number of cubes. So I would say I have a 1/4 chance of drawing a blue cube. Makes sense, right? So is each color equally likely to be chosen? Well, if you go up here, we had 40 total, and it was the same number. So were they all equally likely to be chosen? Yes. Okay. Each color, let's say that, or there's the same number of each color. Okay, there's the same number of cubes for each color. So how do the theoretical probabilities compare to our experimental probabilities? Okay, well, if there's 40 and 10 of each, it should be 1/4, right? 1/4 equals 0.25. So how did that compare to what we drew out? Well, we got exactly 5, right? 1/4, I should say, our probability here. But green was 3/10. Red, 2/10. But blue was exactly on. So it wasn't exactly the same as the theoretical probability, but it was pretty close. So how did they compare? Close, but not exactly the same. Okay, so we were close. It kind of makes sense, and I think the more we drew out, it would get closer and closer to being 1/4 each. Okay, so let's take that idea of theoretical probability, not hey, we're going to do this test a bunch of times and use that, but actually what could happen. So an experiment consisted of flipping a nickel and dime. The first step in finding the theoretical probability of obtaining heads on the nickel and heads on the dime is to list the sample space. Okay, sample space, all the possible outcomes. So I could get a head on the nickel and a head on the dime, right? That's what I want. Okay, does that mean I'm going to get a head on the nickel and head on the dime every single time? Nope. I could get head on a nickel and tails on a dime, or I could get tails on the nickel and heads on the dime. Remember, flipping them in the air, they're landing. Or I could get tails eat, both, right? So there are 1, 2, 3, 4 possible outcomes, okay? Remember, sample space, okay, is all possible outcomes. Now, it doesn't mean that I could do this 4 times and get all 4 of these. No, but that's the 4 outcomes that could happen. Okay, really important to be able to list the sample space because we're going to use that to find the probability. What is the probability of flipping 2 heads? Well, that's once. Okay, that happened once out of how many total? 4. 1/4. Okay, you need to list those outcomes or need to find the total number of outcomes. Find your sample space. You need that number for the bottom. And then you also need to know the favorable outcomes. Looking at them here, there's just one that is right. Okay, so let's keep trying some examples here. Consider a chance experiment of rolling a 6-sided number cube. Okay, dice or die, right? The singular of dice is die. with the numbers 1 through 6 in the faces. What is the sample space? Well, the sample space is to list all the outcomes. It's a six-sided number cube. So 1, 2, 3, 4, 5, 6. When I roll that number cube, one of those numbers is going to be sitting on top. So that's the sample space. What is the probability of each of the outcomes? Put that in a different color here. What is the probability? Well, what is the probability that I roll a 1? Well, it would be 1 out of the total, 1, 6. What's the probability I roll a 2? 1 out of 6. What's the probability of rolling a 3? 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. Okay, because they're all equally likely. And again, we're not doing this a bunch of times and then using that information. We're thinking, theoretically, this is what should happen. Doesn't mean it's gonna, but this is what should happen. So what is the probability of rolling an odd number? So probability of an odd number. We know there's 1, 2, 3, 4, 5, 6 total. How many of them are odd? 1, 2, 3. So 3, 6. Okay, or which reduces to 1/2. What's the probability of rolling a number less than 5? Not less than or equal to, just less than 5. Well, I have 6 total. How many are less than 5? 1, 2, 3, 4. 4 out of 6, which reduces to 2/3. Okay, so we have a 2/3 chance of rolling a number less than 5. We have 50% chance, 1 out of 2 chance of rolling an odd number. Okay, again, that's why listing the sample space is so important, because you can just count what your event is, what your favorable outcome is, and put it over the total. More examples. Consider the experiment of randomly selecting a letter from the word number. What is the sample space? No problem. Let's write out the word number. N, U, M, B, E, R. Now you'll notice in this one, I didn't skip any letters because there's no letters being repeated. There's no 2 U's or 2 B's or anything. So if there was another B, I wouldn't write the second B. What is the probability of each outcome? Well, again, 1, 2, 3, 4, 5, 6. 1/6 chance of doing an N, 1/6 of a U, 1/6, because again, we're randomly selecting a letter, 1/6 and 1/6. So what is the probability of selecting a vowel? Well, how many vowels are there? Because I know there's 6 total. 1, 2. 2, 6, which reduces to 1/3. What is the probability of selecting the letter Z? Well, I know I have 6 total. How many Z's do I have? 0, right? So there is a 0% chance that I'm going to pick Z. It's impossible. There isn't Z to begin with. Okay? This should seem very familiar to what we were originally doing with probability. The new part here is listing a sample space and using it to find that theoretical probability. Last example, pay close attention to this one. Excuse me. Students are playing a game that requires spinning the 2 spinners shown below. A student wins a game if both spins land on red. What is the probability of winning the game? Okay, so our goal is going to be to find the probability of winning the game. Remember to first list the sample space and the probability of each outcome. Okay, and it's telling us there's 8 possible outcomes. Again, pay close attention to this one because you're going to have something like this on your homework. A lot of people want to break this up into 2 things, but you can't. We have this one we're spinning, and then we're spinning this one. Okay, so we're doing 2 things. Let's say I start with red. Okay, I could get red on the first spinner, and I could get red on the second spinner. But I could also get red on the first spinner, and then spin this one and get blue. Or another combination, because again, I'm doing 2 things here, is having red and yellow. Or red on the first spinner and green on the second spinner. So if I get red, there's 4 options that go with it. But what if I get blue first? Okay. Well, if I get blue and then I go to spin the second one, I could get red the second time. Get blue the first time. My second spin, I could get blue. If I spin a blue on the first one, The next one I could get yellow on the second spinner, or blue on the first one, and green on the second spinner. Okay, so you see, these are my 8 possible outcomes. Those are together. Don't think of it as we're going to get red or blue, or going to get red, blue, yellow, green. No, no, no. When I spin it twice, what can I get? Okay, so there's 8 of them. So we know our total's 8. And if I want the probability, okay, actually, let me write that down somewhere else. So I have some more room here, right? I want the probability that both land in red. Okay. So the probability that both are red. How many times does that happen? Just the one time, right? How many total are there? 8. So the probability that they both are red is just 1 out of 8. The big part is being able to write the sample space. Okay? All right. So when all the possible outcomes in an experiment are equally likely, the probability of each outcome is 1 out of the possible. Now, event is a collection of outcomes. Okay? When all outcomes are equally likely, the theoretical probability event can be expressed as the probability of the event, probability both red, is the number of favorable outcomes, in this case 1, out of the all possible outcomes, the total. In this case, it's 8.